Here are solutions to homework set number 5 for ECE 461-61 control systems. This homework set looks at block diagrams, canonical forms, and finding the transfer function for electric circuits. Now the first problem is block diagram. This is what you can expect to see on the FE exam. Given a block diagram, find the transfer function from x to y. And this is actually more complicated than what you get on the FE exam. There's a couple two ways to solve this. The first is use a shortcut. It's going to be numerator over denominator. The numerator is just the gain from x to y. So the numerator would just be the gain from x to y. So here's one path, ABC, this term. Here's the second path, DBC. Here's the third path, EC. That takes care of the numerator. For the denominator, it is 1 plus the loop gains. So here is one loop, BCF. Here's a second loop, BCFG, ABCFG. And that's all I can see. That's one way to do it. On the FE exam, I would use the shortcut. Usually that works. Occasionally it doesn't. The long way that always works is to declare the output of each summing junction a variable. I'm going to call it m and n. Then write the equations. M is x minus g times f times y. N is d times x plus a times m minus f times y. And y is c times b times n plus c times e times x. Once you get the equations, do a bunch of algebra, substitution, time passes, and I get the exact same answer. Problem 2. Another block diagram. Find the transfer function from x to y. Again, the shortcut is from x to y is a, b, c times g. I'm going to call that g to make it easier. Here's the second path, d times b times c times g. That's the numerator. Denominator is 1 plus the loop gains. So here's one loop, BCE. Here's the second loop, BCGFA. And that's all I can see. So I think this is the answer. To check, I could do the long way to find two dummy variables, m and n. M is just x minus f times y. N is d times x plus a times m minus e times c times b times n. And y is g times c times b times n. Do some algebra, substitution, time passes, and I get the same answer. So the second method always works. The first method usually works. Occasionally there's some loops that are hard to see. Problem 3, canonical forms. Given a transfer function, there's an infinite number of ways of expressing that in matrix form or state space form. Give me 2. So one approach is controller canonical form. Multiply it all out, and here's the denominator polynomial, here's the numerator polynomial. If I check in MATLAB, input A, B, C, D, I get the same transfer function. I could use Jordan form. Do partial fraction expansion, and then here's the first term, pulls at 0, minus 2, minus 10. The numerator is 1.5, so this term times that term is 1.5. Second term is 1.75, so this times that is minus 1.75. Third term, 0.25, 1 times 0.25, those two terms. As a check, throw it in MATLAB, and I get the same answer. Third approach, I could use cascade form. Giving a common numerator, I wind up that A is 0, B is 1, C is 30. So here's your cascaded form. First pole, B is the second, B is the third. Here's the numerator. Throw in MATLAB, same answer. So there's the infinite number of ways of expressing a system in state space form. If you see two different people represent it two different ways, don't sweat it. Many ways to represent it. Problem 4. Find the transfer function from V0 to V3 using state space methods. So the first trick is find the currents to the capacitors I equals C dV dt. So I1 is the current from the left. That's V0 minus V1 over 5, plus this current, 0 minus V1 over 80, plus this current, V2 minus V1 over 2. All that together adds up to I1, that's C dV dt. At the second node, I2 is the current from the left, V1 minus V2 over 2, plus the current up, 0 minus V2 over 90, plus the current from the right, V3 minus V2 over 7. And finally, I3 is the current from the left, V2 minus V3 over 7, plus this current, 0 minus V3 over 100. So there's your equations. To put in state space form, solve for the highest derivative, put in matrix form, so SB1 is 20 times V0 minus 71.25 times V1 plus 50 times V2 plus 0 times V3. Repeat for equation 2, equation 3. I'm going to pull off V3. To find the transfer function, throw A, B, C, D in MATLAB, express it in state space form, convert it to 0 poles and gain, and there's your transfer function. MATLAB makes this actually pretty easy. Problem 5. If I change what I'm measuring from V3 to V1, all that changes is the C matrix. Find the new transfer function. Note, the poles did not shift. Previously, the poles were right here, minus 134, minus 35, minus 8. Now, the poles are minus 134, minus 35, minus 8. Poles don't change when you change the output. The numerator changes, the zeros change. That's one of the reasons we ignore zeros in this class. Depending upon what you're measuring, the zeros are going to change. Poles are all important. Poles tell you how the energy dissipates. They tell you the settling time, whether it oscillates. Poles are really what we focus on in control systems. Problem 6. Another circuit. Find the transfer function from V0 to Y. Means Y. So to do that, I've got 1, 2, 3, 4, 5 ways to store energy. I'm going to wind up with a fifth order transfer function. To do that, I'm going to use the capacitors as I equals C dV dt. For inductors, the voltage is L di dt. So for the first one, I1 is just I3 minus I4. The second capacitor, I2, that's C dV dt, is I4 minus I5. The third one, I3, the voltage on the left is V0 minus 5I3. Voltage on the right is V1. Fourth one, voltage on the left is V1 minus 8I4. Voltage on the right is V2. And the last one, voltage on the left is V2 minus 10I5. Voltage on the right is 100I5. So that's your 5 equations, 5 unknowns. To put in matrix form, solve for the highest derivative. Place the matrix form. For example, the first equation, SB1, is 10I3 minus 10I4. Here's your A matrix. Here's your B matrix. Your C matrix is what you're measuring. I'm going to measure Y, which is 100I5. There's your D matrix. Throw that into MATLAB. Find the transfer function, and voila! That's the transfer function from Vn to Y. Problem 7 says, what initial condition makes the natural response decay as quickly as possible? What makes it decay as slow as possible? That's an eigenvector problem. Take your A matrix. I've got eigenvectors, eigenvalues. Here's the fast eigenvalue. Something decays quickly. The eigenvector is what decays quickly. If I pretty much make the initial condition I5, that'll decay as e to the minus 1099t. And that kind of makes sense. Going back to the circuit, if my initial condition is basically 0, 0, 0, 0, 1, this current very quickly dissipates across 100 ohms. That's the fast mode. There's also a slow mode. That'd be this guy right here. That decays as e to the minus 1.3t. What decays that way is the eigenvector. So if the initial condition is 0.48, 0.86, 0.1, that decays slowly. Going back to the circuit, if this is 0.48 volts, this is 0.86 volts, and this is 0.1 amp, then these two voltages kind of slowly dissipate down to zero. And there's three other modes. It's a fifth order system. That's what the eigenvectors tell you. Somebody oscillates. This is what oscillates. And for complex poles, I have a sine and a cosine. Just take the real part, you get cosine. Take the complex part, you get sine. That's kind of what eigenvectors are. So that is homework set number 5 for ECE 461.